Yeah, hello. Welcome to this lecture on estimating parameters of spatial transformations within the lecture series on 3D coordinate systems. The last lectures were about how to represent such spatial transformations, especially rotations, and how to apply them, for instance, when modeling a robot arm. And this and the next lectures we will discuss how to estimate the parameters. So given some point pairs in two different systems, and they are related by some similarity or motion, then we want to know how to best estimate the parameters of these transformations. So let's start. So we want to estimate these parameters, but not only estimate them, but also characterize their uncertainty. Because if you have a black box system and you have uncertain data coming in, you get uncertain data coming out, and we want to characterize the output of this estimation process. And we then, of course, have to take into account that the data may have outliers, so we have to look into this problem also. Let's start with the task. Let's assume we have pairs of corresponding points in two different systems, xi and xi prime, and we have capital I number of points. We assume they are related by a similarity or possibly a motion, and the task is to solve the Helmholtz transformation. The Helmholtz transformation is that transformation which gives the best estimate for the parameters. Friedrich Robert Helmholtz was a geodesist born in 1843, which worked on estimation theory and especially also on these geometric and geodetic problems. So the task is then to estimate the parameters and provide quality measures of the estimation. Now we already start with a problem. Because we have measurement deviations in the coordinates, the relation between the coordinates xi and xi prime, which should correspond, is not perfect. So rigorously seen, this is an inequality. In the following, we only assume that only these measurements, the xi primes, are perturbated by random errors, deviations, measurement deviations, etc., how you call it. And that means we add a correction, v, index xi prime. V comes from Verbesserungen in German, corrections. So we have the corrected coordinates. These are our measurements, we correct them, and then the corrected measurements should fulfill this relation. Now the consequence of this setup is that we have an under-constraint system. So we not only have the 7 parameters lambda, r, and t, which are 7, but also all the residuals, all these corrections which we have here. So we have less constraints than unknown parameters. And the idea to solve this under-constraint system goes back to Carl Friedrich Gauss, which proposed the principle of least squares, which you probably know from mathematics in your first course. And the idea is to determine the corrections and the parameters in such a way that the corrections are smallest. Smallest in this case means if we sum the squares of all the corrections, this sum should be minimal. And this implicitly then gives the estimates for the other 7 parameters. Now there are really solutions. There exist direct solutions, that means solutions which don't need any approximate values and have a limited computing time, fixed computing time, for estimating the 7 parameters of a 3D similarity and the 6 parameters of the 3D motion. So we will see how this works, these two solutions. But the question now, of course, is why is that not sufficient? Why don't you just tell these solutions and then finish? The reason is that the data don't fulfill the requirements that this is the best choice. Let's have a look at the following situations. You have here a LiDAR point, an instrument, which observes this point. And because you have direction measurements and they are uncertain, and you have distance measurements which are uncertain, you have a certain uncertainty ellipse here at this place. If you now change in a different direction, a little bit further away, because it's further away, the angular measurement has a larger influx, so the ellipse is a little bit more elongated. If you are closer to that point, the ellipse is elongated in the other direction. And it may even be very small. So you see it's inhomogeneous and it's not the same accuracy in all directions. So taking residuals in all directions with the same weight would not be the same thing, not a good thing. Now, if you take a stereo setup with here these 2 points A and B looking at this point with the camera, let's say, you have to intersect these two rays, you get an uncertainty area of this type. If you go there, now it's a little bit, only a little bit changed. But if you are at this place, the ellipse is much smaller, and if you are here, it's quite elongated in one direction and not so elongated in the other directions. That means we have to take into account that the uncertainty of the points, each individual point, may be different from point to point. The same also holds for GPS data. If you have GPS data, you have an instrument, then the three-dimensional accuracy depends on how the configuration of the satellites is at that moment when you do the measurements. That means these direct solutions don't take the uncertainty of the observations into account. The given points may have different accuracies, as we have seen. They may have correlated coordinates. That means the ellipses need not be parallel to the axis. And they may even be correlated among each other. For instance, if A and B are determined by some means, and the relation between A and B is uncertain, then all the points which you derive by stereo are correlated. The same holds if the point O in the LiDAR case is uncertain, then all the points inherit this uncertainty of the observation point. So in general, we need to take into account all these different types of uncertainties. And the second is that these direct solutions do not provide any uncertainty about the estimated parameters. There is no covariance matrix for the resultant parameters. So the task is really, we have to look into how can we take the uncertainty of the given coordinates into account, and how can we then, if we do the estimation, derive the uncertainty of the estimated parameters. Now, the task of estimating parameters is a very general one. So we have a geometric environment here with similarities. You may have a different environment if you look for motions of satellites. You may have a different application in physics. You may have a different applications in chemistry. So there are many application areas where you want to do parameter estimation. And on the other hand, there's the world of estimation, which the statisticians have built up. So they start from some measurements which are given, some observations, and they have, on the other hand, some unknown parameters which they want to derive from these measurements. And of course, they are some way related. And that means we need to look for that the notation in these two worlds probably overlap. For instance, we have here the coordinates x, and here if we take this convention, L are the observations and x are the unknowns, then we have an overlap between the coordinates and these unknown parameters. If you go into the literature, you find different conventions. Many statistical textbooks work with y as the observations and beta as the unknown parameters. You also find, especially in the machine learning, that x are the observations and theta are the unknown parameters. So depending on the community, you have different ways to describe estimation problems in general. So what we want to do is, of course, we would like to take this world of estimation and look into the estimation theory and then apply it to our application. In order not to get confused, we leave the notation in both worlds and make assignments. For instance, if we use the convention that L are the observations and X are the parameters in the world of estimation, then we start from the observed coordinates and the unknown parameters and make an assignment that our observations L in the world of statistics are all our observed coordinates, and the unknown parameters in the world of statistics are the parameters P of our, let's say, transformations. And as soon as we have done the estimation is denoted with a hat, then we say the estimated parameters of our application is assigned as the value of the estimated value X in the world of statistics. So we leave the notation in both worlds, and we have to be careful that we make clear in which world we write our equations. So let's have a look at the principle of estimation. Let's assume we have given some problem with unknown parameters. We usually have some idea how these parameters are. So if you measure a point in Bonn, you know you are in Bonn, so you have approximately the latitude and longitude of Bonn with some inaccuracy of, let's say, a few kilometers. So you have a prior idea, which is uncertain, about your parameters of that point. And then you do observations, let's say with a laser or with a camera, and then you know, of course, how good your measurements are from your measurement specification, or you have analyzed your instrument, so you know the uncertainty of your observations if the unknown parameters would be given. So these are the two basic information where you start, and the task is to find those parameters which best explain the observations, taking all this information into account. So we could say the estimated parameter is that parameter X which maximizes that X which has the highest probability given the actual observations. So this would be our general setup of our estimation process, and now we have to find out how to do this. And there is this famous theorem from Bayes, which actually says that if you have this prior information, P of X, and you have this probability for our observations, the distribution of our observations, if X is given, normalized with P of L, gives the posterior probability of X given L. This relation actually, though it's a famous theorem, can easily be derived from the law of conditional probabilities. So the joint probability of L and X is nothing else than the conditional probability of X given L multiplied with P and L, and you can exchange L and X. So we start from P of X. Then we have the likelihood of X, that is this function, the probability of L given X. That's so to say how likely are our observations which we actually made if X is given. So this is a function of X. The posterior distribution is a distribution of X given these values L, and because these values are measured, we have given them, they are some fixed values. This is a sample, so to say. We have the probability to observe this specific set of observations, so this is a constant. So if we want to optimize this posterior probability, we just have to we maximize the probability, we just have to maximize this product. We don't have to take this denominator into account. This leads us to what is called the maximum a posterior probability. So we have a maximum posterior probability estimate. Sometimes it's also called Bayesian estimate. Some people are careful in making a distinction here because they say Bayesian estimates take some costs into account. So what is the estimate which leads to the minimum costs as a consequence of our estimation? So the MAP, maximum posterior probability estimate, is that X which maximizes the product of these two probabilities. And because this is the likelihood function, you could also say it's the likelihood function multiplied with the prior on the parameters. Because this is usually much narrower, more higher accuracy, it will override the prior probability. But let's assume you have made a measurement of a certain point yesterday and you remeasure it today, assuming it's not moved. Then of course you would expect that you get some weighted average between the values yesterday and today, which is actually then the base for incremental estimation like Kalman filter. Now, let's assume you have no prior information, or you assume I don't care about what the x is, which is in a very, very large range. So as you assume that p of x is a constant in the range where you work, then you arrive at what is called the maximum likelihood estimate because it maximizes the likelihood function of x. You remember, this is the probability of the observations given the x, and so you get here different estimates. You see the difference is it's just that there is no prior here. Now, the third assumption is that you say, let's assume that our observations are Gaussian distributed, which is a reasonable assumption in many cases if you don't have outliers. And secondly, you assume that the relation between these observations and the parameters is a linear one. So you have here a linear relation between L and X, and the difference between these two follows some Gaussian distribution, which I wrote down here. You see here A needs to be given, X is unknown, and you need to know the covariance matrix of your observations. So this leads to what is called the best linear unbiased estimator. That means if you have this assumption, you can find an estimator which leads to the smallest covariance matrix of the estimates. Second, the estimate is a linear function of the observations, which is nice. And the estimate is unbiased. That means you have no systematic errors in your estimate. And that means you, instead of maximizing this probability, you minimize this expression. So the smaller this expression, because you have here the exponential, you get this optimization. This looks much like least squares if we omit this part. So the last part is if we just have no weights, we get the difference between our observations and the linear relations between the x and the l's with this a times x, a is a given matrix. Then if you take this minimum, then you have the ordinary least squares, because this is these differences are actually our corrections of our observations. So this is, so to say, the description of the Gaussian principle in the notation which we use here for the estimation theory. Sometimes people say, okay, we do some weights in here. So we weight each individual residual and we have a weighted least squares. Sometimes people say this is a generalized least squares with some weight matrix. So what you have seen, we have specialized the original estimation problem such that at the end, with all these conditions, we arrive at ordinary least squares. So this leads to a hierarchy of estimates. So we have here the maximum a posteriori estimation, the maximum likelihood estimation, the best linear unbiased estimation, and the least squares estimation. We come from here to here, from the Bayesian estimation to the maximum likelihood estimation if we don't have priors. We come from here to the best linear unbiased estimation by assuming that we have a linear model, A times X, and we have a Gaussian distribution. And finally, if we just don't think about it in statistics, we choose the inverse, the weights to be the inverse covariance matrix, we arrive at some least squares estimation, which can be interpreted just geometrically. So the least squares could be said, I have a point in space and a plane somewhere, and I look for the point which is closest to this plane. This is the geometric setup, which I don't want to go into more detail. If you want to take some uncertainty into account, you can do with the best linear unbiased estimation, where you minimize the variance, because here you only need the first and second moments of your observations, of the distribution of your observations. That means you only need the mean, that means the model, and you need the covariance matrix. This is sufficient if you want to do variance propagation, because variance propagation doesn't require that the data are normally distributed. And finally, if you want to do testing of your residuals, for instance, to find outliers, you need to have a stochastical model. That means you need to specify the distribution. Then you actually arrive at the maximum likelihood estimation, and you need to do this in this framework. Now that means if somebody says, I do ordinary least squares, looking at this hierarchy, you can say, this is maximum a posterior estimation without prior, assuming Gaussian distribution, and always are 1. So you can interpret a least squares estimation in terms of a statistical view using this specialization hierarchy, which I wrote down here. Okay. We now come to our problem a little bit more closer, because what we have is a nonlinear model. The model is nonlinear because we have a product of lambda, the scale, and the rotation matrix, and the rotation parameters are going into the rotation matrix in a nonlinear fashion. So we have a nonlinear Gauss-Markov model, and the Gauss-Markov model has the following form. We have the observations actually explicitly described in this form. That means we have the likelihood function described in this form. Now, this means we fix the mean value, which is then non-linearly dependent on x, and we have the covariance matrix, which may depend on x, and we assume a normal distribution. So this would be our setup. Observe that we have here an underline. That means if we have a stochastical variable which is distributed following this distribution, we underline the variable. If you have a sample of this variable, we don't underline it because it's not stochastic anymore. If you do a reading of a coordinate on a coordinate measurement machine, you get a certain number and that's fixed. So the functional model which we have is the following. We say the expectation of our observations given the unknown parameters is some generally nonlinear function of x. And the stochastical model is the dispersion, that means the covariance matrix, of our observations given the x, which is actually the dispersion of the observations minus the f of x. You see here the x comes in here into this definition, which we call sigma, the covariance matrix with index LL, because it refers to L. Actually, I should have written down here constraint on x. So the mathematical model for our estimation consists of this functional model, which refers to the first moments, and the stochastical model, which describes the distribution. Here we only specified the covariance matrix of a normal distribution. Now we can rewrite this model in different ways to understand what actually happens. So let's assume we have this function of x given, and let's assume we know the parameters. Then we can derive f of x. Then we add some perturbations and get perturbed observations. So this would be an equation which we would use for a simulation process. We generate ideal observations, so to say the expectation, add observational noise and get the real observations. And you see here the covariance matrix is actually referring to these perturbations. We could also say we have these corrections. So L plus the corrections is the ideal observation, which depends on X. And then we have L plus V, and we have here the covariance matrix of the residuals. And of course, because this is just the negative of the other, the two covariance matrices are here the same. And now if we have a look at the covariance matrix of our observations, no, this is a fixed value. The covariance matrix of L is the same as the covariance matrix of the E, the errors, and the same as the covariance matrix of the residuals. That means this covariance matrix of the L's actually refers to the disturbances, the perturbations of our observations, or to the residuals, the true residuals, if we would know the mean value. The mean values are fixed values, so we have this very rigorous relation. So there is no uncertainty in the L's, only that of the perturbations. So now let's have a look at the maximum likelihood estimation of our problem. So the likelihood is nothing else than the conditional probability of L given some values X. So we have said, this is a Gaussian distribution. That means we have to minimize this optimization function, or in other words, the sum of the residual squared weighted with the inverse covariance matrix. That means if we want to do generalized least squares in a statistical framework, we need to choose the weight matrix for our generalized least squares as the inverse covariance matrix of our observations. Now, we go to the specific case for the Helmholtz transformation. We look for the stochastical model, for the functional model, and then for the stochastical model. We look at a general model, and then we have to discuss how we can simplify it. So, we have observations, coordinates. We have assumed that the transformed coordinates are measured. That means they are perturbated, and we put them together in a long vector. That means these are 2 or 3 vectors depending on the dimension. So we have here the I observed coordinate vectors. We put them in a large vector, which is then called L, which has length n. This is standardized to n. And we have, of course, the individual observations. And the n, the number of observations, is the dimension multiplied with the number of points. And of course, we have the corresponding corrections. In the same way, we have residuals or corrections to the coordinates of the observed points. And we put them in a long vector, which of course has the same length. The second is we have to look at the parameters and the functional model. So we have here the unknown parameters collected in a U vector. In this case, U is 7. So we have here the 3 rotation parameters, the 3 translation parameters, and the scale parameter, which is a 7 vector then. And the functional model is the expectation of our L the nonlinear function of x. Or if we write it in the application notation, the expectation of this vector x1 prime is lambda times r times x1 plus t. And that's for all the other points also. Now you see we have left something open, namely how to represent the rotation matrix on one side, or how this vector r actually looks like in relation to this rotation matrix. So this is not exactly the same thing. So we have to define this in the context when we do the estimation really. At the moment, the representation of the rotation is open. Now let's have a look at the stochastical model. The stochastical model says specifies how the observed values L, that's an n vector, are connected with each other. So on the main diagonals we get the variances or covariance matrices. For instance, here we have in 2D we have a 2 by 2 covariance matrix of the first point which we observe. And here we have the ith and the jth point, etc. And that means in 3D we have a 3 by 3 matrix, and if we have let's say a GPS measurement for point x1 prime, then this in general will be a full 3 by 3 covariance matrix. Symmetric, because it has to be symmetric covariance matrix of a point. That means the coordinates may be correlated. They are covariances. So this is the diagonal part of this covariance matrix. Then we look at the off diagonal. This is the covariance of the first point with the ith point. That means the x-coordinate of the first point and the x-coordinate of the ith point are in some way related statistically. This is described in this covariance matrix. This covariance matrix in general is unsymmetric. And of course, here we have the transposed for the covariance matrix. So in generally, we have a very large matrix. So if you have 1,000 points in 3D, we have 3,000 observations. And we would need to specify a 3,000 by 3,000 matrix, which is probably not what we will do in general in our applications. So let's make a drastic simplification. Let's assume all the points are mutually statistically independent. That means we have zeros on these off diagonal elements. Second, we assume that all the coordinates at one point have the same accuracy. X, Y, Z have the same accuracy and are uncorrelated. But for each point it may be a little bit different. So we may have a very precise point, or we may have a very bad point, and we describe that by this factor sigma x1 square, which is the variance of the first point coordinates. So this is a very simplified model, and you see we don't need to specify much. We only need to specify the sequence of these variances from 1 to I, and we are finished, which is very simple. Now, how does this relate to the previous case visually? Let's have a look. This would be a very general situation. So we have here 5 points, and each point has an individual standard ellipse here, here, etc. They're all different. They have different directions. They have different size. Even what I don't show here in the figure, they may be even correlated. So this would be the situation if the covariance matrix would be full. If the points are not correlated, so each individual point is independent of the next point, then we would have a block diagonal matrix for the covariance matrix. But each submatrix would be full and different. On the other hand, we could say all points have the same accuracy. That would be this case. That means they have the same x uncertainty, the same y coordinate uncertainty. The x and y coordinates are not correlated. And this would be the most simple way which we could think of. What we described just now would be a situation where the individual points have different uncertainty, but the x and y coordinates of each point have the same accuracy, and x and y are uncorrelated. Now you see, here we have a situation where the accuracy varies with space. That's the same as here. So each point has a different accuracy depending on its location. Whereas in this case, the location has no effect. Now, if you look here, we have a uncertainty relation which is this isotropic. That means direction independent. If you rotate the coordinate system, it has no effect onto the uncertainty of the coordinates. This is not the case here. So we could also think of a specific case where the accuracy, the uncertainty configuration is homogeneous. That means each point has the same accuracy, but it's anisotropic. That means it's direction dependent. This might be useful in certain cases. For instance, if you have a small area which is very far from your laser, then all these points may have an uncertainty which is ellipsoid type, but it will be more or less the same. So this may be something which happens in practice. In the following, we will discuss this case, and that means we have weights which are inverse to the variances, 1 over the variance of the individual points. So we have each point has an individual weight. So this is the situation which we will discuss in the next lectures. So that means the optimization problem is simplified. So what we have here, we want to estimate that rotation, translation and scale, which minimizes this optimization function. And the optimization function is the residuals of the first point, of the ith point, minus the predicted point. So lambda r xi plus t would be the predicted point. The difference is the residual. We take the transpose. That means this will be the sum of squares, and the whole sum is weighted with one scalar, namely wi. So we have a very simplified problem. It's still nonlinear, but it's much easier to handle probably than what we started with. It's a nonlinear problem because of these relations. So there are different types of solutions. There's of course an optimal solution for the general stochastical model. This yields the covariance matrix of the estimated parameters. Because we have a maximum likelihood estimation, we can look at the posterior distribution, that means of the probability distribution of x given L. Of course, we can simplify the stochastical model down to the very most simple model with same variance for each point, for each coordinate. The disadvantage is that this general solution needs approximate values. It's an iterative procedure. That means depending on the quality of the approximations, we need more or less iterations. That means the computing time will depend on the quality of the approximations. Now, the interesting thing, which I already mentioned, that we have direct solutions for the simplified stochastical model. That means for exactly this problem, which is useful for two things. First, we get good approximate values, and if the stochastical model is sufficient for our purpose, we are already done. And the second is that if we have this solution, we can look what the optimal solution would say about the quality of the resulting parameters and use this result to characterize the result of this simplified direct solution of the simplified model. And we will see that we will have a very fast solution for 3 points, which we will need if we do outlier detection. So this is the program for the next lectures. We will start with the direct solutions for the simplified stochastical model next time. And thank you very much for listening.